Uvamnut billua viulauqtoq peqataujuullualaorama aulartartilluta. Takuyaqtoq talaukkavut ikpingnallua vilauqtoq takuyaulauqimangimata. Kinga yui angitchaamealauqmata ammalu hangmiyuit angitchaamearlutik kuungillu kuurjuatchaamearlutik. Aukpalliajorlu kuungorpalliabluni nangarnallua vilauqtoq. Aulaqateqalaorama uyaraaleriyinik ilitchivigilau miyakka. Qauyimangilautunga napaartoqalau qimanneqma qangatchaamea million ukiu. Ajjileorinermillu ilitchivalaurlungattauq taamna quveeginerpaaqalaurtara puiguleigara inuhilup taamni. Puigulangitarattauq ilataakka amma nunau katjaarnaarninga.
Canada has so many pristine natural environments, and as a child, I was fortunate to spend time each summer traveling to different parts of the country and to explore these areas camping with my family. I was and still am amazed at the variety of beautiful environments we have here in Canada. This expedition was an incredible opportunity, not only to travel to one of the most remote parts of the Earth, but also to study a time in the Earth's history during the Cretaceous where things were changing in ways somewhat similar than they are today. It's awesome to be part of this expedition and to do research that's just so important as the Earth's climate and geography is changing, and I'm really excited to share my experiences and our discoveries with you.
Working in the North as a geologist is one of the best things I ever did in my life. I studied geology in the 1990s in Bochum in Germany, and my supervisor during that time gave me a book to read about Cretaceous climate from Edwin Kemper. The chapters about the Canadian high Arctic climate within this book and all the figures in black and white inspired me since then. So I feel really privileged that I can now work as a geologist in the Canadian high Arctic because, you know, unlike most other areas of the world, it still remains relatively untouched and there's plenty of room for new scientific discoveries. This is in particular true for the Cretaceous high Arctic successions we want to study, a time period where Earth's climate was in a really extreme greenhouse mode compared to today.
For over 20 years have I studied rocks and fossils from the Cretaceous period. People ask me what I do, and I often say that I reconstruct ancient landscapes, which requires many different disciplines. And those disciplines then require, in turn, a very good team, and that team I have here with me. I take great pleasure in taking students, the next generation of polar researchers, into the field. And I feel that's a very rewarding side of my job as a professor. The Arctic, as we know today, is in great flux. This film will show the viewer how it has changed always through geological time. And that is really very exciting for us to discover and to research.
The Arctic summer is full of surprises. Unpredictable weather can change flight conditions in the spur of the moment. The team has flown from Ottawa to Resolute Bay, an Inuit hamlet on Cornwallis Island, and home to the logistical headquarters of the Polar Continental Shelf Program, or the PCSP. Here, all the gear will be checked one last time. Plans for camp moves are discussed, and the team enjoys the delicious cooking of the friendly PCSP staff. The researchers will head to Axel Heiberg and Ellesmere Islands to investigate how the Arctic has responded to past greenhouse phases of Earth climatic history. This film will take you back to an Earth without the large ice caps as we know them today. mission of the expedition is well defined. Earth climate can be subdivided in phases of icehouse and greenhouse periods and intermediate stages in between these two extremes. Our globe's climate history was never stagnant. Even though we presently have large ice sheets on our planet, although melting at a rapid rate, we are still in icehouse conditions. As we go back in geological time, much warmer periods persisted on our planet, allowing ecosystems to thrive that were very different from those we know today. One of these intriguing warm periods is the Cretaceous period, 145 to 66 million years ago.
First question we have to ask, why are geologists, climate geologists interested in a time which is far away from us, 100 million years, 120 million years ago? That was a very peculiar time in Earth's history. And you would say, well, that's too far away from modern days. Then I usually tell people that when we stop at the gas station, we fill the tank of our car with gasoline, with this yellow fluid. We look at it and we say, well, fantastic, we can drive another 500 kilometers. We should not forget that this gasoline is sometimes 50, sometimes 100 million years, and quite a bit of our gasoline was formed in Cretaceous times. So we should sort of be thankful that the Cretaceous time was a very peculiar period in Earth history. It was a time when about 30% of our fossil fuels were formed.
These are luxury shales. Look at these.
Maybe. I hope that they're Oh, Jesus.
Yeah, not bad.
That and a hot cup of tea in my hands? Oh.
Yeah. You know what? Without having a share.
Claudia, Jens, Alex, and Keith.
flight towards the Stacy icefield reveals spectacular landforms. Valleys on both sides of the fjord are occupied with Piedmont glaciers that spill onto the coastal region. The fjord itself was carved out by one massive glacier that has retreated since the last ice age. The Cretaceous age sediments exposed along both shores were once deposited in a marine basin that covered a large part of the Queen Elizabeth Islands. These islands were under an ocean 110 to 80 million years ago, telling a story of a much warmer Earth. An Earth where sea level fluctuated and tectonic forces were at play. A sedimentary basin preserves ancient sediments, which provide the evidence for past environments and their inhabitants. This basin is named the Sverdrup Basin, in honor of the Norwegian explorer Otto Sverdrup. In the late 1800s, Sverdrup charted 260,000 square kilometers of these Arctic islands and overwintered several seasons in this northern land.
Spread out.
We are not alone in the valley. A herd of musk ox grazes on surrounding slopes. These animals are acutely aware of our arrival. The herd stays their distance, but remains a welcome neighbor doing our work at Glacier Fjord. This species of musk ox is the tundra musk ox, a species that originated about 10,000 years ago.
The Cretaceous was also a time, and that's why we are studying the Cretaceous in these days in great detail. It was a time of what we call greenhouse climate. PCO2 levels, CO2 concentrations in the atmosphere were probably twice or 3 times or 4 times as high as today. And that's why, of course, it's very interesting to learn more about Cretaceous climate and the impact of special Cretaceous climate on life, on the oceans.
Geologists subdivide the Earth's rock record into formations that are described by a characteristic rock type and fossil assemblage that can be regionally mapped. Formation boundaries are placed where rock types change or where gaps in the rock record are detected. Those gaps can be caused by exposure, which allows for erosion or lack of overall sediment deposition. The chronological order of these formations are summarized in a stratigraphic chart. The first day brings the team to the Isaacson Formation, which roughly covers the Hoderivian to the Aptian stages of the Cretaceous period. The exposure of the Isaacson Formation is greatly enhanced by the retreating glacier, exposing a fresh rock face for the geologists. The Isaacson Formation represents a phase when the Sverdrup Basin was relatively shallow. The formation is dominated by thick layers of sandstones that are interbedded by coal-rich, finer-grained layers. Careful investigation of these layers has determined that an ancient delta is exposed here, A good example for a modern delta is the Mackenzie Delta, at the intersection between the mighty Mackenzie River and the Arctic Ocean.
At the moment, we are sitting on what we call the Isaacson Formation. The Isaacson Formation is a very large deltaic complex. It starts off with a fluvial, so river-influenced delta, so at the upper end of the delta. And then we are going through a increasingly marine phase, and that's what we are sitting on here right now, which is the so-called Rondon member of the Isaacson Formation. And then as we continue our journey onwards, we are getting back into a deltaic complex, but the more marine influenced part of the delta. So there's, right away, we see with the rocks we are seeing here, with the sedimentological structures, with the trace fossils, we can see how actually throughout time this particular area has changed.
This section here, the Rondon member, is a big discussion how old it is. And we try to date this with carbon isotope records, and I made just a little drawing for you. So this is the whole Cretaceous, starting in the Berriasian, Valanginian, Hutterivian, Barremian, and the Aptian interval, up to the Turonian. And actually, we can study that here in the Arctic on Axel Heiberg. And this is here a carbon isotope record with 0 per mil here, 4 per mil here. And you can see that there is a nice pattern with major positive excursions in the carbon isotope record at the late Valanginian. And then we have a major negative shift here in the Aptian and a major positive shift. And then we are going up to the Cenomanian Turonian, where we have another positive carbon isotope excursion. And we studied this section 3 years ago in a very low resolution, but we found a very strong negative delta 13C excursions just here within the Rondon. And this is why we think maybe this is lower Aptian in age. And this negative excursion followed by a positive one, this is an interval what we called the Oceanic Anoxic Event 1A. This is a global event where the water masses, in particular the deep water, turned anoxic. So no oxygen in the bottom waters in the oceans. And this is, you will find it in the Pacific Ocean, in the Atlantic, South and North. And I believe that we also find it here in the Rondon member, in this shallow water environment, where we have all these nice, what we would call paper shales. Yeah? So you can take it and it falls in pieces thin like these little papers. And the advantage of studying that is that every single layer, every paper, you can read it like a book. So what you can do is you take a piece out of it and you can do organic geochemistry on it, you can study microfossils on it. So we found at least some here. And for example, you know, if you have the papers here, our microfossils and the organic geochemistry, this would be the letters and the words. And this is how we do geology. Yeah, we can read the rocks.
What Jens was saying is really interesting too. Like in the global scale, there are areas where the sea bottom becomes very anoxic, so no oxygen. Now, in this particular section here, which is really representing a shallow water shale, we are not suddenly going into deep water here between these two deltaic sand packages, but a shallow water, we do not have anoxia. And that is what we can, the evidence for that is this interval is very rich in small organisms which are called foraminifera. And foraminifera, benthic foraminifera, are one-cell organisms which are very abundant in marine to brackish settings. And this particular section has a very low species diversity. It's mainly 1 or 2 species, but they occur very abundantly throughout this section. So there are so animals, so one-cell animals. That means that they need oxygen, and it tells us that this area was not completely anoxic. But we are still seeing this major isotope record, so there's an interesting puzzle for us to resolve as our analysis then continues and carries into the laboratory.
The Isaacson Formation holds many secrets which are discovered with careful observation. A delta is an environment where a flowing river loses its energy as the river enters the ocean. As the energy subsides, particles that the river carries get deposited. This ancient river carried abundant wood, as we see evidence for petrified wood in these sandstones. And if you take a look at the present surroundings, not a single tree is to be found. But way back in the lower Cretaceous, this land was covered by rich forests, and with that, we have already a clear sign that the Arctic was much warmer and had a completely different ecosystem.
We learn now that sometimes extreme volcanic activity on the planet triggered these what we call greenhouse episodes. Through volcanism, maybe through some other processes, a lot of CO2 was transferred in a relatively short time to the atmosphere. This makes a greenhouse effect. And it seems, said in a sort of simple way, that this greenhouse climate, among other things, triggered an increase in marine productivity. If you have an increase in marine productivity, suddenly more algal material is sinking through the water column, and under peculiar conditions, when waters become oxygen-free, organic carbon can accumulate in sediments at a higher rate than usual. And then you have these black sediments. Anoxic conditions, how we call them, probably occurred because of increased flux of this organic carbon to the water column. Decaying organic carbon sort of consumed oxygen, and oxygen was missing at a certain point in the deeper water.
The team has reached the boundary between the Hassel to Bastion Ridge formations and the Bastion Ridge to Kanguk formations. Since these ancient seabed layers are tilted through tectonic forces, it is almost like one can walk through ancient time.
So what we're sitting on right now is called paper shale, and it's called paper shale because of the way it looks and the way it parts. If you have a look from the side, you can see it breaks in these sheet-like structures. You can just keep prying them apart thinner and thinner. Now, at the time of deposition, this package was being deposited in a distal shelf setting, so the sediments that were being deposited were fairly fine. And this was happening around the Cenomanian-Turonian boundary in terms of time, which at that time there was an oceanic anoxic event going on, which means that below the surface waters, the water was devoid of oxygen, which means it couldn't support life. And as part of my honors thesis, I looked at the microstructure of these to see if there was any evidence of oxygen. So what I looked at was microbiotubation, which is the reworking of primary sedimentary fabric by organisms. So I did this by using a scanning electron microscope to look at the microfabric of these paper shales to see if there was any distortion by the reworking of these sediments when they were eating their way through looking for food. And what I found was there was a very dominant parallel orientation of all the particles, which means that they were aligned the same way as when they were deposited. So they weren't reworked. There were no traces of organisms, which is another supporting element to the idea that there was no oxygen.
With the exception of a few large mammals, Today's Arctic ecosystem is observed on a small scale. Clumps of small plants grow close to the ground, which protects them from the cold, strong winds. Their growing season is short, so their flowers need to be produced very quickly. Cup-shaped flowers or dark flowers attract the sun's heat. But for flowers to thrive, insects are needed for pollination. In the summer, only a few centimeters of the ground is unthawed, so roots are shallow. As the Arctic is a desert with little rainfall, leaves of plants are small in order to retain the moisture they need. What type of vegetation did the much warmer Cretaceous Arctic support?
After a day's work, we have many questions. What were the environmental drivers that determined the ecology of the Cretaceous polar ocean? How did polar life respond to the extreme warm conditions that affected Earth globally around the Cenomanian-Turonian boundary, the level of the oceanic anoxic event 2? Was marine plankton dominated by siliceous groups, such as diatoms and radiolarians? So far, we have found very little carbonate in our sediment samples. What caused the lack of oxygen on the seafloor during the anoxic events? With future analysis, we hope to shed some light on these questions.
Today the team moves to a new locality called Lost Hammer Diapier. There might be a lost tool to be found from geologists who explored and mapped here over the last 100 years. Stig, the helicopter pilot, arrives and the team needs 3 loads to move the camp. Once more, the flight takes us over the measured sections of the Cretaceous and provides an impressive view of the end moraine of the glacier as it sheds its sediment into Glacier Fjord. The flight takes a northwestern direction along the glacier that is part of the Stacy Ice Cap.
As I sit in this modern helicopter rushing over the glacier, I'm compelled to think about the pioneers of geological exploration. Without their extensive work, we would not perform ours. Mapping activities by the Geological Survey of Canada during the 1950s and 1960s as part of Operation Eureka and Operation Franklin produced valuable maps used today. During those years, Ray Tornsteinson and Edward Timothy Tozer, 2 survey paleontologists, had their base at the Eureka Weather Station on Ellesmere Island. As they traveled by canoe and dog sled, their work was limited to shoreline regions. Later, during Operation Franklin, a Piper Super Cub was outfitted with wide, soft tires, and bush pilot Valent Phipps brought them further inland. I'm in awe of the immense scale these men operated on and the work they accomplished.
The locality the team is heading for has an excellent exposure of the lowermost Cretaceous with its boundary to the underlying Jurassic period. Some interesting questions arise when working at this locality. We can predict what the Earth was like during the lowermost Cretaceous from research done in low latitudes. From this research, abrupt changes in ocean sedimentation have been observed. Carbonate platforms with lots of carbonate-secreting organisms collapsed and abruptly turned to black shale without carbonate.
It's cleaning itself.
One local resident, an Arctic hare, has made the stony desert its home. This hare seems to be a loner, although large groups of several hundred individuals can also be encountered in the Arctic. The Arctic hare lives all over the Canadian Arctic north of the tree line. It does not hibernate in the winter as it is well adapted to the harsh climate for surviving on lichens and woody plants such as willows that it finds under the snow. Arctic hares are nocturnal. They rest during the day and feed in the evening and into the night. The genus Lepus has been found in the fossil record as old as the Pliocene-Pleistocene boundary, approximately 2.5 million years ago. Camp moves are exhausting days, but a solid shelter in this environment is a necessity, and so everything needs to be safely stored and secured. The team builds the camp with a view of the Deer Bay Formation, the section they want to measure. There are not many distractions in this harsh environment except the stark beauty of the land itself. The camp is surrounded by rocks of the Cretaceous and the underlying Jurassic periods.
Yes, we have now, when we talk about these anoxic events, over wide parts of the oceans, we find sediments of Cretaceous age, which are black sediments rich in organic carbon. But we can go to other areas in the world's past oceans, in these Cretaceous oceans, where we do not find black sediments, but we find carbonate. But interesting enough, during times of like shale formation, the deep ocean, we sometimes have in shelf oceans evidence that carbonate production suddenly came to a halt. We call this a biocalcification crisis occurred, coinciding with these oceanic anoxic events. How do these two things go together? And it seems that's at least one possible explanation. They're not only elevating nutrient levels in the seawater, but also elevated CO2 concentrations in the surface water made calcification for organisms, for certain organisms, much more difficult. A calcification crisis. Some people talk even about acidification of oceans during oceanic anoxic events. Something which will be of great relevance in 100 years from now, when all models indicate that we will have dramatic calcification crises, shallow water settings, reefal settings, because of elevated CO2 levels in the ocean.
We are coming down the Deer Bay Formation. It is the unit that forms the basal formation of the Cretaceous period in the Sverdrup Basin. But what is really of interest here is that these Arctic sediments were deposited during the same time as these dramatic changes occurred in lower latitudes. So we need to understand if the Arctic reveals also a change, and if so, of which nature and what would have triggered the change.
Thank you.
Germany 7-1, 7-1.
So we are even lower than this. We are Verrassian.
Ja, also das ist
So why is it so special that we come here to the high Arctic and study, for example, the Cretaceous period, which is the main goal of our science here? It's because there is no vegetation, and so everything is exposed in front of us, And the only areas we cannot see, of course, are glaciated areas where the ice sheets are still covering the rocks. We see this really nicely over here. We have a major ice sheet here. As the ice retreats, as we see far in the distance, as the ice retreats, which is of course during large melting phases, which we can see in recent years, we get rock surfaces freshly exposed. And so we geologists, we go there, and there we can see actually some of the strata particularly well exposed. But let us just take a look where we are standing on here. This field of sandy rubble is part of the Isaacson Formation. And as we look in this direction, way through this major valley, we are getting younger and younger in geological time. And so we're standing here on the Isaacson Formation, which is a dominated sandstone formation. It is a large deltaic deposit, so a major fluvial and marine delta was at this time in the Arctic. And as we then get through the valley, we see that the sediments become much finer grained. And we're getting into these black shale intervals and black to gray shale intervals, which means that the basin, and we are looking here at the Sverdrup Basin, that the basin is becoming deeper. And with that, we are getting deep water deposition away from the shoreline where we get all the sands. And with that, we are having fine-grained sedimentation throughout this valley, and that is the so-called Christopher Formation, another lithological unit which geologists have here described. So then we go further, and we are going all the way to the yellowish, light grayish cliff face beyond the shale unit, and that is the Hassel Formation. The Hassel Formation is, again, a shallowing event of this basin after the major transgressive and deepening event of the Christopher Formation. And so we're getting into the Hassel Formation, which is sandstones deposited again, either deltaic or along basically a shore face. And in this particular locality, it is of great interest. The Hassel Formation is capped by a very black band, as you can see, and it is sort of leaking down into these various valleys. And that black band is of volcanic origin. It is a volcanic eruption which is bringing a basalt flow, basically blanketing the area with a large basalt flow, and that is the so-called Strand Formation. The Strand Formation is of great interest to geologists and volcanologists, and it is part of what is called here a large igneous province. And this particular one is the High Arctic Large Igneous Province. The Strand Formation is one of the upper flows, the younger flows of the so-called Halle.
And I think these volcanic activities, which are so typical also for the Cretaceous, they were probably very important. These huge, large, so-called large igneous provinces forming at a certain time in Earth history. And this is interesting because we learn now that processes of the Earth interior and processes of the Earth's surface or of the biosphere are strongly coupled.
Good evening, Tim. This is Lost Hammer Camp. Over.
Yes, good evening, Claudia. How did your day go to see you today? And do you have any traffic for us this evening?
Yes, Tim, I just wanted to call you after SCAT to discuss the logistics for the move tomorrow. The weather is turning. Thick fog rises from the valley floor in record time. We become even more aware of the silence and extreme remoteness of this place.
Clouds are hanging low this morning, and the flight to the next locality on Ellesmere Island has to be executed in several stages. The Mars Field Station of McGill University at Expedition Fjord serves as an intermediate refuge between camps. The helicopter is heading towards a locality south of Slidre Fjord, and Stig chooses the Eureka Pass to cross the Princess Margaret Range. As the team flies over the southern extent of the Mueller ice cap and look down on a glaciated landscape, thoughts return to the Cretaceous greenhouse climate.
Very important, accelerated burial of organic carbon is also accelerated pumping of atmospheric CO2 from the ocean atmosphere into the sediments. Because we all know that photosynthesis is an interesting process. CO2 is fixed in organic carbon during photosynthesis. And solar energy is stored in the organic carbon. Organic carbon is buried, CO2 is taken out from the atmosphere, and the greenhouse climate is, over millions of years, stabilized at the level which is acceptable for life. So when we go to our gas station, let's go back to this picture, and then we drive the car, we use solar energy of the Cretaceous for driving our car. The only problem then is that we also liberate carbon dioxide stored in this organic carbon and add it to the modern atmosphere. Worse, the greenhouse climate of the Cretaceous in modern days, except in the Cretaceous, these episodes lasted millions of years, and mankind brings back the CO2 to the atmosphere in hundreds of years.
I just arrived here to rejoin the group at Slidre Fjord. After 2 nights with the very nice people at Expedition Fjord, I was stuck there due to fog and rain. So now it's time to dry out all my stuff and get back to work.
In front of the campsite is a complete section of the Anoxic Formation that holds the secrets of the late Cretaceous period. The most striking feature of the cliff is the abundance of light-colored beds, which represent the bentonite beds, interlayered with shale. These are ancient ash falls that had turned into soft clay over time. The frequency and considerable thickness of these ash beds attest to the explosive nature of volcanism that had marked this Cretaceous phase of Earth history. As volcanic eruptions had persisted over thousands of years, more and more greenhouse gases were added to the atmosphere, and the Earth warmed, to which polar life had to adapt.
Yeah, here's something we have been looking for at this entire section. We're coming through, 200 meters of shale, and we find a bed here, or several beds, which are rich in one particular fossil, a bivalve, so a shelled fossil. And these very delicate shells are preserved here, made out of calcite crystals, or prisms, better term for it, prisms. And the species is Phenoceramus patutensis. Now, we are excited about this particular layer here because this is giving us the more or less the position of the Santonian-Campanian boundary. And it is a marker species, so a biostratigraphic marker species, all over the Arctic region. And in our project here, we have found now this particular fossil at the same stratigraphic level in 3 different localities. At our Glacier Fjord locality, where we were at the beginning of our journey, on Elfringens Island, which was the previous expedition, and now we find it here. And with finding this fossil in the field in all these different localities, we can really nicely correlate these sections, and particularly at this particular level.
The team carefully samples the bentonite beds. The chemical composition and the geochronological age from these samples might provide linkages to the various phases of the high Arctic large igneous province and the opening of the Arctic Ocean. Ash, the very finest component of a volcanic eruption, can travel extremely far depending on wind systems and the strength of explosion. An ash layer, if preserved in the geological record, provides a short-lived snapshot of a catastrophic event, which leaves a mark on the paleo-ecosystem of that time. How did Cretaceous Arctic life respond to these catastrophic events?
So here we see the end of our Kengak Formation, and we can see a really nice sharp boundary here between a black shale interval, which is still the underlying Kengak Formation, and a white sand here, somewhat altered into a yellow, but then getting into a really white sand of the overlying expedition formation. And this obviously represents a major change in a sea level. We are going from a distal shelf environment into a coastal environment and into a deltaic environment. And this boundary here could be a boundary where a considerable amount of time is missing. That is often very difficult for geologists to determine the exact missing gap, but one would need fossils for it, one would need more geochron ages, but this certainly is a boundary which we would call conformable, where the history of deposition is completely preserved without any gaps. So we take that as an example for our presentation in Resolute to the community at the community day, or the open house from Polar Continental Shelf. Very nice. 45, 46.
The expedition comes to an end. The team is bringing over 1,000 sediment samples that need to be packed up for shipment to come south by barge. These samples should hold the answers to the many questions that had evolved from their field observations. It has been a tremendously successful field season. This research will improve our understanding of how an ancient Arctic marine ecosystem had responded to the Cretaceous greenhouse climate.
At the end, we have 10 and 13, 23 buckets of material. Oh, no.
Slider Fjord, no Slider Fjord. Good evening, Claudia. How's everything there tonight?
Good evening, Tim. This is South Slider Fjord. We are just fine here.
And I was wondering if weather and schedule allowed to pick up our sample buckets at Sherwood Head. Over.
Unfortunately, at this point, that's a negative. Have yet to do that, but that is on the top of our list of things to do. How on that?
That's great, Tim. I just wanted to send a reminder. Wet and prickles. We are aware and should all be concerned about the rapid loss of Arctic sea ice in recent years. We have seen it with our own eyes coming to these localities. Yet, as we study planet Earth and its climate system through deep time, we discover that climate change is not a recent phenomenon. In order to make reliable future predictions, climate models still need much improvement. We hope that our work will advance our understanding of past ecosystems and their adaptations to climate change.
Ame hunu tau tugau ma hilau at yarong na ihumaluk tau bluni ukiok tak tumiu taman na kau yimalak kaming nitar maroni ilanamni nakkarlutik inuyun ne kimalak tu ukiu pingahut kanyak tunik kau yimang itunga hilau at yarong nernut pip mangati kiheni kau yimayunga hila hikulo nalunak himata tukihe himat chaopta at yarok palyaninganit pang nangnak himat chayu luar tugut ilin nertuni nunak yuap ngunang nerelaukanik tau kovenak tok ilit chiyor sungalo.
Gratitude for all the support we received, making our journey successful and unforgettable. The people of Grise Fjord, who granted us access to their homeland, and the so very capable staff and pilots of Polar Continental Shelf, who brought us where we needed to go, deserve a special mention.